Welcome. In this lecture, I'm going to quickly go over igneous rocks and some basic properties that you need to know about them. So all igneous rocks are crystalline rocks that form from the cooling and mineral growth from lavas and magmas. So they are associated with volcanoes, which is why we're looking at a little composite volcano here. Igneous rocks can be broken into two major types. We have intrusive and extrusive igneous rocks. Intrusive rocks are those that are forming and cooling within the Earth's crust. So they're a little bit deeper, think 5 kilometers down below the Earth's surface. Now these are the ones that are cooling and crystallizing from magmas. So what we can see here is a little magma chamber that's rising up. We call these things, the blobs, they're called diapirs. And as they start to cool and crystallize, it takes a very long time. Think, thousands of years for these things to crystallize, hundreds of years. So as they're crystallizing, they're going to slowly grow and form these really nice big crystals, and those crystals are going to be interlocking. They tend to be larger in size, and these make up those coarse-grained igneous intrusive rocks. Okay, so we find them at the Earth's surface, like we see down here. This is Torres del Paine down in Chile. So these beautiful spires, these were once deep down under the Earth's crust. Weathering took all those rocks away, and then they were lifted up. So then they're exposed now, and people can go climb on them if they want to. Okay, the opposite of an intrusive rock is an igneous extrusive rock. So we're looking at a picture of a lava flow in Hawaii. So this is where the lava is cooling and crystallizing very, very rapidly. So the time period we're looking at no longer years, thousands of years, even millions of years, but this is very quick. This can be hours to days to weeks to cool and crystallize. So when that's happening, the crystals are growing all at the same time. The crystals tend to be very small. They're hard to see with our unaided eye. So we say that they're fine-grained or igneous extrusive rocks. So they're also sometimes called volcanic because they're coming from these lava flows. So what's happening when a magma is crystallizing? So the crystallization process, we're going to start out with a magma, and inside of that magma we have what's called the melt, or the ions that are present. We do see some little bits of solids. These can be mineral bits that are pre-existing, maybe things that have gotten picked up by the magma or the lava as it was moving through the crust. And then we have a lot of gases, which include water, carbon dioxide, and methane. Now all of the ions start to come together in a very specific way that creates that orderly pattern, and our mineral crystal starts to grow. Okay, and again, as we noted before, the rate of cooling can be slow, fast, or super fast depending on where it is and what's going on. When we start to try to identify our minerals, and you can pick up sample 20 if you have it in your kit, there are two things that we look at. The first is the texture. We want to know, are the mineral crystals big or small? And then the second is what minerals are present. What do you see? We're actually looking at a piece of a granite, which is very similar to your sample number 20. This is coarse grains, so the individual grains are over 2 millimeters in diameter. We can see them with our eyes, and then we'd actually go through and start to identify, the pieces of quartz, the different feldspars that we see. All right, igneous rock textures do tell us where the rocks are forming, and it's all determined by the speed of crystallization. So we've already talked about those fine-grained or aphanitic rocks, or coarse-grained or phaneritic rocks. We have porphyritic rocks. These are those that have 2 grain sizes, and then we also have some that are glassy. I'm going to go through each very quickly. If we want to look at an aphanitic rock texture, you could pick up sample 17 out of your lab kit. This is basalt, which is also shown here in this image. You can't see any individual grains because those mineral grains were cooling very quickly, again, from a lava flow at or near the Earth's surface. Okay, so these are your igneous extrusive rocks. Okay, you could pick up your granite again, sample 15. This is a phaneritic or coarse-grained rock. It's an igneous intrusive rock. It's forming in the crust. So, a couple miles down, kind of 5 to 10 miles or so, if you want to think about depth, 20 miles. And you have mineral grains that are bigger than 1 millimeter in diameter. You can see them. And again, the grains are about the same size overall when we look at it. A vesiculated rock texture, if you were to pick up sample number 25, this is scoria, which you can see here on the right. This is a sample that has lots of holes. These vesicles or holes tell us that gas was escaping very rapidly as that sample was forming. These form crystallize under very rapid conditions at the Earth's surface, and the bubbles vesicles tell you that gas was escaping at the same time. Glassy textures are those samples that have no mineral grains but are made up of glass. So sample 21, this is obsidian, which you can see over here on the left. Okay, this is not a mineral, but actually an igneous rock. There are no minerals present. It's amorphous. There's no specific chemical structure. This cooled very, very rapidly. Usually in contact with water will often create this obsidian, and it creates that smooth glass structure. Pumice is another sample that you can see glass. If you look at this under a microscope, you'll see glass blades, glass shards. This forms very rapidly when it's ejected out of a volcano. All right, porphyritic textures are those that have two very distinct grain sizes. So your sample 16, if you look very closely at it, you'll see some bigger grains. These actually still happen to be small, but you'll see some bigger black grains surrounded by a really fine grained matrix. This is called porphyritic texture. These textures happen where the magma was cooling at depth in the Earth's crust. It started to form those bigger mineral grains, and then before the whole thing had crystallized, the magma was brought up to the surface with the pre-existing crystals, where it then cooled very rapidly to form that fine grained matrix. So this represents two stages of cooling. So in the crust and then out of the crust before it all ends. All right. Now, igneous rock compositions, what we're showing here are a couple of the different minerals that you see. These are the common rock-forming minerals. And again, we finalize our igneous rock identifications by investigating which minerals are present. We can see a couple here. Quartz tends to look very glassy when we look at it. Our micas are very shiny and will have a flaky appearance to them. Biotite and muscovite are both very common. Olivine is very green and glassy. We start to see this in our peridotite or ultramafic rocks. It has high iron and magnesium content, so it's darker in color. We have, excuse me, our augite or pyroxene. This one, when you look at it, will be black and shiny and have a blocky appearance, while our amphibole is going to have a black, shiny, and splintery appearance. Amphibole is also called hornblende. And then we have our feldspars. These tend to be blocky. They can be any range from grays to whites to even pinks, depending on which type of feldspar you're looking at. So is it potassium feldspar or plagioclase feldspar? Okay. Felsic minerals are those that are generally light in color. So we have three that we've listed up here. We have our feldspar, our mica, and our quartz. These have the highest concentrations of silica. They also tend to have potassium, sodium, and some calcium. Mafic minerals are those that are generally dark in color, so they have more iron and magnesium in them. They have a little bit less silica present. So three minerals to know would be olivine, your amphibole, and your pyroxene. Okay, would go in that category. Now, minerals tend to form under very specific temperatures and pressures, and so they sort of form in groups. On the cool end of things, we see more minerals that have silica. They are higher in potassium and sodium. They have less, but this is trying to show here, less calcium, less iron, less magnesium, and more silica. So quartz, potassium feldspar, sodium-rich plagioclase, and biotite are all minerals that are forming at higher up in the crust where temperatures are lower. If we go a little bit deeper down and we're at higher temperatures, we start to see more plagioclase feldspar. We're getting into the calcium-rich plagioclase. We see amphibole, so more of the ferromagnesium minerals, and this forms our andesite, our diorite, our intermediate compositions. Basalts tend to have pyroxene and calcium-rich plagioclase. These are more mafic. And then on the very far end, when we start to see lots of olivine, maybe a little bit of plagioclase, a little bit of pyroxene, we'll start to see those ultramafic minerals. So what this is just telling you is that our minerals that tend to be more high in silica form at lower temperatures. Our darker colored minerals tend to form at higher temperatures. All right, so we're going to go quickly through the four major compositions you need to know. Felsic means that it's high in silica, so think of really light colored minerals, a lot of quartz, a lot of feldspar. It has maybe 10% of the darker colored minerals, a little bit of biotite giving that darker color. Sometimes we'll see some hornblende or amphibole in there as well. These are a major component of the continental crust. Granites are very common in convergent plate boundaries where we've seen some magma diapirs crystallizing to form that granite. We do see a little bit of rhyolite if that has been erupted as well, not quite as common as some other rocks. Our mafic composition, so if you wanted to pick up your basalt, which was your sample 17, and you wanted to compare it to, I think my samples are all mixed up right now. You can compare that one to your sample 19, which is going to be your gabbro. These are both darker in color. Okay, they have a lot of the pyroxenes and maybe some olivine might be present. You'll see some feldspar. You will not see any quartz. These make up, the basalt makes up the oceanic crust. So if we go and dig down into the oceanic crust, we'll see basalt. If we go deeper into the oceanic crust, we'll start to see some gabbro. Okay. Intermediate compositions, if you not want to pick up your sample 18, this one I like to call the salt and pepper rock. As my kids say, they call it the Dalmatian rock. You've got white minerals and black minerals that are kind of 50-50 in there. So this is an intermediate composition. Diorites you can see sometimes in continental convergent plate boundaries, but the andesite, so your sample number 16, kind of a light gray, medium gray color. Let's get the light just right. Okay, andesite is much more common. We do see it at those convergent plate boundaries. So that's going to be the more common igneous extrusive rock that we see. Okay, and then we have our ultramafic rocks. This is a beautiful sample that we're looking at in this picture. The green glassy mineral, again, that's our olivine, and the black mineral is going to be your pyroxene. And that sample, did I just move it? Would be sample 22 if I didn't get them all mixed up. Yeah, sample number 22. And if you look very carefully at yours, use your hand lens. I'll hold that up just to remind you to look at that closely. To do the hand lens, hold the hand lens to your eye and then bring the rock sample up into focus. You want to have a lot of light hitting the surface, and you should start to see some green glassy olivine in there. So these ultramafic rocks, these are associated with the mantle, so deep down, and occasionally parts of the mantle that have crystallized get brought up to the surface, and that's when we see these peridotites exposed. All right, the last thing that I want to show up here, and I'm not blocking the table, so there's nothing behind my image, but this is just a really nice way to organize all of the igneous rocks that you need to know. So by their composition up here on the top, going from felsic to ultramafic, and then their texture. The big key to remember is that when we're talking about felsic rocks, the coarse-grained intrusive rocks is your granite. The extrusive equivalent is rhyolite. Okay, so they go together. They're the same composition, just different textures. We have diorite and andesite, gabbro and basalt, and peridotite. If you're having a hard time keeping track of these rocks, this would be a good table to write down and to keep easily referenceable in your notes. With that, that's everything that you need to know about the basics of igneous rocks, where they're forming, and how to tell them apart. If you have any questions, please post them to the I Need Help discussion.